Line voltage is indeed the 208 volts measured between two phase legs in a three-phase system typically found at the main panel within a building. Line voltage is the potential difference existing between any two line conductors in a polyphase circuit. In a three-phase system, this voltage is often referred to as the phase-to-phase voltage. It's the voltage that would be present if you were to connect a voltmeter between any two of the hot wires coming into the panel, excluding the neutral or ground. Phase voltage is the 120 volts measured between any one phase leg in the neutral bus bar or grounding bus bar. Phase voltage, on the other hand, represents the voltage between a single phase conductor and the neutral or grounded conductor in a power system. In a three-phase system, this is often called the phase-to-neutral voltage. This is the voltage you'd measure if you connected a voltmeter between one of the hot wires and the neutral wire in the panel. The relationship between line voltage and phase voltage in a balanced three-phase system is that the line voltage is equal to the square root of 3, which is approximately 1.732 times the phase voltage. In a 208/120 volt system, the phase voltage is 120 volts, and when multiplied by the square root of 3, you get approximately 208 volts, which is the line voltage. Understanding this distinction is crucial for several reasons. Firstly, equipment selection depends on knowing the correct voltage. Many electrical devices are designed to operate at a specific voltage. Using the wrong voltage can damage or destroy the equipment. For instance, if an appliance is designed for 120 volts phase voltage, connecting it to 208 volts line voltage would likely cause it to fail. Secondly, proper wiring and grounding are essential for safety. Incorrectly wiring a circuit with the wrong voltage can create a fire hazard or electrical shock hazard. Grounding the system correctly helps to protect against these hazards. Thirdly, troubleshooting electrical problems often requires measuring both line and phase voltages. Unusual voltage readings can indicate a problem with the electrical system, such as a loose connection or a faulty transformer. In a commercial building, the main panel is typically fed by a three-phase transformer. This transformer steps down the high voltage power from the utility company to a lower voltage that can be used by the building's electrical equipment. The main panel then distributes the power to various branch circuits throughout the building. Each branch circuit is typically wired with a phase conductor, a neutral conductor, and a grounding conductor. The phase conductor carries the current to the electrical device, while the neutral conductor returns the current to the source. The grounding conductor provides a path for fault current to flow back to the source, which helps to protect against electrical shock hazards. When working with electrical panels, it's important to take precautions to avoid electrical shock. Always turn off the power to the circuit before working on it, and use insulated tools. If you're not comfortable working with electricity, hire a qualified electrician. When measuring voltages, use a properly calibrated voltmeter. Make sure the voltmeter is set to the correct voltage range before taking a measurement. Connect the voltmeter leads to the circuit points where you want to measure the voltage. Be careful not to touch any bare wires or metal parts while taking a measurement. Always double check your readings to make sure they're accurate. If you're unsure about anything, consult with a qualified electrician. Understanding the concepts of line voltage and phase voltage is essential for anyone working with electrical systems. By following these guidelines, you can help ensure the safety and reliability of your electrical system. Further considerations include the National Electrical Code, or NEC, which provides guidelines for electrical installations. Article 220 covers branch circuit, feeder, and service calculations. This article specifies how to calculate the minimum size of conductors and overcurrent protection devices for various types of loads. Article 230 covers services. This article specifies the requirements for the service conductors, service equipment, and service disconnecting means. Article 250 covers grounding and bonding. This article specifies the requirements for grounding and bonding electrical systems. Grounding helps to protect against electrical shock hazards, while bonding helps to reduce the risk of fire. Article 300 covers wiring methods. This article specifies the requirements for installing electrical wiring. Wiring must be installed in a safe and workmanlike manner. Article 310 covers conductors for general wiring. This article specifies the requirements for conductors used in electrical wiring. Conductors must be sized correctly for the load they will carry. Article 400 covers flexible cords and cables. This article specifies the requirements for flexible cords and cables. Flexible cords and cables must be used only for specific applications. Article 430 covers motors, motor circuits, and controllers. This article specifies the requirements for motors, motor circuits, and controllers. Motors must be protected from overload and short-circuit conditions. Article 440 covers air conditioning and refrigerating equipment. This article specifies the requirements for air conditioning and refrigerating equipment. Air conditioning and refrigerating equipment must be installed in accordance with the manufacturer's instructions. Article 500 covers hazardous locations. This article specifies the requirements for electrical equipment installed in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Other key areas in electrical systems include transformers, which are essential components in electrical power distribution systems. They are used to step up or step down voltage levels to efficiently transmit and utilize electrical energy. Transformers operate on the principle of electromagnetic induction, where a changing magnetic field in one coil induces a voltage in another coil. The ratio of the number of turns in the primary and secondary windings determines the voltage transformation ratio. Transformers are designed to operate at specific voltage and frequency ratings. Overloading a transformer can lead to overheating and failure. Proper cooling and maintenance are essential for reliable operation. Circuit breakers are protective devices designed to interrupt the flow of current in a circuit when a fault or overload condition occurs. They are used to protect electrical equipment and prevent fires. Circuit breakers come in various types and ratings, depending on the application. They are designed to trip quickly to minimize damage to equipment. Regular testing and maintenance of circuit breakers are necessary to ensure proper operation. Ground fault circuit interrupters, also known as GFCIs, are designed to protect people from electrical shock. They monitor the current balance between the hot and neutral conductors in a circuit. If there is a difference in current, it indicates that current is leaking to ground, which could be a shock hazard. GFCIs trip quickly to interrupt the flow of current and prevent a shock. GFCIs are commonly used in wet locations such as bathrooms and kitchens. Electrical meters are used to measure the amount of electrical energy consumed by a building or appliance. They are typically installed by the utility company and are used to calculate the monthly electricity bill. Electrical meters measure energy in kilowatt-hours or kWh. Understanding how to read an electrical meter can help you monitor your energy consumption. Power factor correction improves the efficiency of electrical systems by reducing the amount of reactive power. Reactive power is the power that oscillates between the source and the load without doing any useful work. Power factor is the ratio of real power to apparent power. A power factor of 1.0 indicates that all of the power is being used effectively. Power factor correction can be achieved by adding capacitors to the electrical system. Surge protection protects electrical equipment from voltage surges, which can be caused by lightning strikes or other electrical disturbances. Surge protection devices, or SPDs, are designed to divert excess voltage to ground. SPDs are typically installed at the service entrance of a building. Harmonic mitigation reduces the distortion of the voltage and current waveforms in electrical systems. Harmonics are caused by nonlinear loads, such as electronic devices. Harmonic distortion can cause overheating of equipment and can interfere with the operation of other electrical devices. Harmonic filters can be used to reduce harmonic distortion. Electrical safety is of paramount importance when working with electrical systems. Always follow safe work practices to avoid electrical shock and other hazards. Wear appropriate personal protective equipment, such as insulated gloves and safety glasses. Use properly insulated tools. to energize circuits before working on them. Never work on live electrical equipment unless you are qualified to do so. If you are not comfortable working with electricity, hire a qualified electrician.